So I'm Michaël Wierlewski, one of the organizer, and yeah, today I will present some of the work. Let me just quickly so I see my screen. I can't actually. Oh, it's fine. And yeah, some of you who attend this conference maybe have seen some sort of an ersatz of that talk because we're still ongoing work. But I'm going to go back to yeah, what we're trying to do in the lab for yeah, maybe the last 5 years, something like this, and the work have been a collection of smaller works, which are mostly dedicated to try to understand how to use the sense of touch in robots and how to use that to mimic how people are actually grasping objects. And what we found is by using very simple metrics in the tactile deformation scene, that we can be super efficient and have very simple controllers that are very robust to grasping different objects with different weights and friction. And yeah, and as we saw before, there's like a lot of needs in robotics to manipulate. I think this is one of the most important things to do, and usually it's done in structured environment, as Vito mentioned, and then more or less we are moving to unstructured environments such as agricultural. And the idea here is that we need to robotics needs to conform to the object, which are always different, which have always different surface properties. And the approach so far has been to use compliance. So Vito showed an example, which was very nice, very thin. It just wraps around the object and capture. And it works quite well, but still, sometimes you need more force, you need more precision, and the rigid approach is still quite used. But in a sense, what's really hard is that the objects we encounter in those environments are mostly changing in shape, changing in softness, changing in texture, so very different mechanical property at the contact level. And in particular, what is really difficult is to handle slippage. So sometimes you can have a stable grasp and then some moisture will come in, and then all of a sudden the object will start to slip. And of course, detecting and reacting to that slip is what we do all day by just grabbing objects without really noticing. And what has been done, so this is one of the example from Lepora's group in Bristol. What's been done usually is that the robots are using tactile sensing, such as the tack tip here, to react to this slippage. And so touch here supports the grip regulation, but at the current time, so this is one example which I think is really cool. They have this tack tip, and then they're filling up this sprinkle can. And what we see is that the sprinkle can, because it's heavier, starts to slip, but then the tactile sensor detects it and regulates or grasp a little bit harder to catch the sprinkle can as it falls. But it reacts to slip. And if you think about, when you are with your glass of wine tonight, if somebody fills up your glass, you will not wait until the object is actually slipping to regulate. You will predict, you will anticipate that it's going to slip. So this is what you're trying to do, trying to really understand how from touch we can anticipate the slippage. And when we started working on it with Laurence, who is here, we went back to the old papers and to the paper from Johansson and Westlin, and that they did a very simple experiment where we just lift an object and looked at the different forces that were involved. And in particular, this is the load force. So it's essentially, initially, it's a zero load force, and then you lift. Load force goes to the weight of the object. But what's interesting is that you get a grip force, and they put different, they put different texture on the object, and the grip force is different depending on the texture that is. So the grip force will start by we start by squeezing, and then while you lift, you will squeeze a little bit more, and then you plateau to maintain the friction, the coefficient of friction. And what we see is that for sandpaper, for instance, which is a high coefficient of friction, you will get a lower grip force than for silk, which is very slippery and where you need more grip force. And so that makes a lot of sense on the right of the graph. But for us, we find that often, what humans are doing is that we put ourselves at about 20% safety margin. So we have a safety margin of grip with grip 20% higher than what by what it's needed to just maintain the grasp. But what surprised us with Laurence and Invar's is that there's this part here, which is quite interesting, where before there is even any load force, human already adapts to adapt the grip force to the friction coefficient. So even before there is tangential force that will measure anything, there is already an adaptation. So we must human must draw some information from the contact to actually find out that that coefficient of friction. And what if we can use, we can design robots to do that as well. So yeah, what I will talk about is like what's happening at the beginning here, the initial contact. I also talk about how we think we detect this safety margin. Okay, so initial contact. So what Laurence built is this very funky device with another PhD student, Jocelyn Monnoyer, and which has a lot of stuff, but essentially what you can do is measure the contact area, the real contact area, via frustrated refraction. And it can also measure the topography of the skin very finely. So it allows us to track how the skin deforms and as we press. And so we have these two illumination. And the plate on top can change friction at will. So we can change from very high friction, so 1.2 coefficient of friction, down to almost 0. And the way that plate works, so I think most of you are familiar with it, it's ultrasonic friction modulation. So the idea is that we vibrate up and down at ultrasonic frequency, and the video is very jittery, but what it shows is that you can stick and you can slip. So when the vibration is all the way on, you have completely a slippery surface, and when it's off, it's like glass, so it's pretty sticky. And we made some measurements, and it shows very well that the friction goes always down. And we also explained that because what it does is that it detaches the skin from the surface by ultrasonic levitation. If you want to try it, we have a better version of that as a demo on Monday. There's a bunch of games which work like this, but it's also active, this one. And so coming back to what Laurence was looking for, which is this expansion of this friction at the very beginning of the contact, what she looked is that we were pressing on those surfaces and look at the images, and on the left what we see is the real contact that actually develops when it's high friction, and it's real contact that shows that is responsible for the adhesion. And on the right we see that there is little movement as we press, so the skin sticks to the surface and doesn't quite move. But then now when we have the low friction, the story is a little bit different. So we see that on the left, the contact is very much darker. So there's less points, there's fewer asperities, fewer junctions that are made. But on the other hand, now the skin is able to actually expand, and that expansion is actually quite radial. So there's no force that is the resulting force from that expansion. And so we were super excited because it means that maybe this was encoded in this deformation. So Laurence ran a psychophysics experiment where she asked, to compare two levels of friction, and she showed that it was pretty easy for participants to. It was pretty easy. It was still a difficult perceptual experience, just pressing and feeling the friction, but people were able to nonetheless perceive it. And so there's some people that perceive all the time. There was more friction in one end than on the other. And what we looked at it is we look at the difference between the comparison, which was very slippery, and the reference, which was very sticky. So a lot of friction. And what we see is that the more the difference between this divergence, the more expansion we get, the more people are able to perceive that slipperiness on first touch. And so that looks a little bit like this. So there's very few displacements when we have high friction coefficient, and when it's lower coefficient of friction, there's a lot of displacement, and that displacement also correlates with the perception. So we're quite happy with this results. And the estimation that we think is that so one of the problems we had at that point is to say, well, we have a small deflection of the skin. So the skin actually moves a little bit, and it's moving behind the background of, you pressing, so that whole hemisphere of your fingertip pressing down on the surface. So the question is really, how does, that small deformation can compare to the big deformation of the fingertip? And what we think is that there is some loops which are running where you can sense the information and some regulation, but in somewhere in the nervous system, there is some sort of map that tells us, like, look at this actual movement, and we can project what we sense to this map and sort of remove the background and remove and get only the expansion of the skin. Of course, it's probably going also to the perception, and what happened is that this map is actually, so this is all the hypothesis, but it's perhaps updated as we move via the efferent copy, by the inverse model that we can have. And one of the hint we have that this is how it works is that if you do the same experiment, but participants are not active, you don't get a perception at all. So it really means that you need to have this movement, this voluntary movement to pre-compute, to predict how the skin will deform, to be able to extract just that tiny deformation. Okay. So safety margin. So remember, when you hold the object, you are 20%, you're pressing 20% more than what you should, just to be at the limit of friction. And we asked ourselves, like, is the safety margin maybe encoded in a similar way with these patterns, with these maps of deformation that are pre-encoded as well? And when we look at the literature, what we know is that incipient slippage is a gradual transition. So we go from full stick to full slip by a gradual diminution of the stick area. And this deformation also of the skin depends on friction. So we see, like, an example. I think I can run it again. Yeah, we see that it stays stuck in the center, and then it disappears on the outside. This is quite a nice video. And yeah, what we think is that this deformation, when we start to slide, we have a coefficient of friction, which is actually local, and the center will remain stuck because it's not outside of the coefficient of friction, but the external part will start to slide. And we know that this also induces some deformation of the skin, some strain in the finger pad. So can we find these stereotypical? And this is what we did. We measured a lot of finger sliding as well. So the images are a little bit crunchy, but and what we did is that we tried to find what are the principal components of that deformation as people will slide, with different level of friction, again, different velocity, different condition. And what we find is that very few principal components, or very few mode of deformation, are actually enough to predict how the skin, how the safety margin, how far are we from the safety margin? Yeah, how far are we from slipping? And so what Laurence did as well in this is to take that strain field and then use those principal components to project on it. So you could take any strain field from the measurements or from the tested data and classify the friction safety. And that works really well, in a sense that we, even with 3 bases, we could discretize the safety margin in 5, and we had a classification rate of 80% with a standard SVM classifier. Yeah, it's interesting to say that if you put the whole data set in the classifier as training for the classifier, it will actually fail to classify correctly the data. So having this dimensionality reduction is actually useful for classifying. Yeah, and so the idea is that we think there is also, in this aspect, the same way that in additional contact, we have these maps that we perceive. And now what we're trying to do is really to say, well, if we have this way of computing quickly in our brain, the strain field, which is rather complicated, can we use the same approach to use that for control and for rapid control of grippers? And the idea here is, like, any problem in grasping is really to to make sure that all your fingers are not slipping and that the object is not slipping from grasp. So again, like knowing your coefficient of friction and maintaining your force vector in the cone of friction. And yeah, one of the way or the problem that we're facing is that when we touch any random object, any arbitrary object, we will have a deformation which is going to be quite complex. It will depend on many things, but on curvature, on the softness, on friction. But what we try to do is like to have some assumptions, so based also on the ideas of Vincent, and to have this assumption that somehow what we're looking for is to find some invariant on friction from that U field and the deformation field, knowing that we have an indentation as an input. So we try really to measure that 3D deformation. So both the normal deformation and the shear. And at the beginning, we were looking for a sensor that could do that. We couldn't find any, so we said a little bit, optimistically, let's build our own. And so we ended up with this idea of having a bunch of markers which can easily translate. So you can easily find a shear component with the markers, and they will be captured by a camera, and so you can find the shear pretty well. But what we struggle with the camera is to figure out how much they move normally, so how much normal force you could have. And the idea we had is just to very simply have two sets of markers, and that this marker will interfere somehow, like the kind of filter with color. And by looking at the color, we would encode the normal deformation. And so she worked on this for a thesis. And what you see is that the color on the left will change on the marker. And from the shape of the marker, shape of the colors, we can reconstruct quite high density set of points. So it allows us to get that huge field, that strain deformation field. And of course, we started looking at can we reconstruct fraction on initial contact like we did with human actually are doing. And so what we did is just using a CNN, very simple machine learning method, and we subsample this image that we had, and had by 5 by 5, and trained that the network to actually recognize if it's a high friction, low friction, or no contact. And we started to press it against random object we found. We trained it with very simple contact probes, so mostly spherical. And we trained it with high friction and low friction only. And then we showed it different shaped indenter, so mostly square across here. And we see that it does some sort of a job to recognize, but it does recognize that it's high friction on the left and low friction, so it's red, it's almost about to slip. But then we did something a little bit more interesting, I think, is that we took random shapes as well, and we put some lubricant only on one side of the object. So half of it was quite sticky, quite grippy, and the other was slippery. And as we touch, we see that even if it wasn't trained to it, it actually detects the friction. And of course, we can reconstruct with shapes, so it allows us to, on the first touch, kind of reposition the gripper if we need to, if we sense that the grip is not strong enough. So we built a gripper to try that, and this is work with Dirkian, and also Laurence were contributed in this. And the idea is that they train also that sensor. So I don't know if it's going to show, but they train and they try to figure out what is the safety margin, try to figure out if from the displacement of this marker, they could actually find. So they painstakingly had this setup where they just slide random, flat surfaces, curved surfaces with different level of friction, and train an algorithm, train a CNN to do that. And again, the idea was to say, well, we have now a knowledge of the coefficient of friction. Can we figure out the safety margin out of it? Even if the object is unknown, even if the coefficient of friction will change, can we figure out the safety margin, which is invariant to the contact properties? And again, we trained this layer. So the idea is that the two cameras were set to a CNN. That's, yeah, it's kind of a black box, dark magic approach, but it gives us nice results to extract this very simple metric. So we have a one-dimensional metric at the end, which is safety margin. And what we see on the right is that this is an actual measurement, and then you get the prediction. You get a prediction in blue, which is not bad at all. And the good thing is that it works. So the good thing about this machine learning approach is that we train it in such a way that we can give it any object and it will work nonetheless. And then when we have that, the control is actually extremely simple, right? So you see in manipulation literature, you see people working on super complicated control because they don't have that metric of the tactile sensor. They don't have that idea of what a friction is. So they come up with very robust approaches. But for us, it was like a real P controller, the most basic thing that could work, and actually performs really well, even with basic tuning. And the good thing is that you can give it any object, so sharp, round, small, big, slippery, no, not, and it will hold it, and it will hold it even if you press on it, if you poke it. Yeah, so this is kind of the example, kind of taking an inspiration of what Lepora has been showing as well with the Springer Con, but this time with a TU-Dev cup. So the first one shows like when you don't have that safety margin controller, and you just have the regular force control that might be. And so now if you put the same, but with the safety margin, I hope this shows pretty well. So you see some adaptation, so you still struggle a little bit. There's still noise in the system, but overall, like he finds a solution. And what you see is that when you start pouring, it will start to grasp automatically. It will start to detect that the object, that the safety margin goes down, and that the object might be slipping, and so react to it. And of course, you could grasp strawberries, and the same thing. Like now, what we can show is that if we have external perturbations, it will also react. Does it show well? Yeah, it shows okay. And so it will react. It will react directly. And so that allows us also to tune how robust we want our grasp, and so how delicate it might be as well, right? Because if we set the set point of the safety margin down to 10%, it will squeeze very lightly. It will be very gentle with but with more risk of dropping the object. Gentle with the object. So here you go, bananas as well. Yeah. So just to conclude, I work really start by the basis that if you want to manipulate, I think it's not a surprise for this crowd, but if you want to manipulate, you need touch. And I think for long, robotics has been looking at compliance. Robotics have been looking at deformable structures. But lately, there's more and more excitement actually in touch in robotics. And I think that's great, because the sense of touch has a lot to bring stuff that visual processing will never bring. So it's important for us, sure, but it's important for robots, sure. And I think my take is that in the whole complexity of what's trying to synthesize what touch is, what is really the main challenge for me is, and for my group, is really to understand how friction evolves and how friction dependent contact gives us, ideas on how to regulate. Yeah, so what we show is that we work really on initial contact during grasping, and now we're moving to what happens when we start to manipulate object and have controlled friction, essentially. And yeah, the last thing is, we see some approaches which also say that machine learning is a black box and not always great, because we don't quite understand what it is. And I think it's also, in this case, I think it's also beneficial in the sense that we have a pretty good idea of the physics, but it's if we want to model that physics to all the objects we're going to encounter. If we want to have a physics which is robust to different aspects of, you know, friction, texture, it's actually super hard, right? It's a problem which is long and tedious. But machine learning is actually very good sometimes if you know the physics and you use machine learning to kind of bridge the gap between the simplicity of the contact mechanics and the complexity of the real world. It actually is very, very beneficial. And I showed you like one example where we generalize, and I think this is great. Yeah, and I would like to thank the group, in particular the work was from Shirin, Laurence Villemette, and Dirk Bustra, and Giuseppe Vitrani also is working here. And Invar is also like was a phenomenal collaborator on this journey. Yeah, thanks.
Any question?
Yeah, go ahead.
Well, it's maybe something that I missed. It's fantastic. I really liked it. The device that you showed at the end, the robotic device.
Yeah.
Maybe you said it. So the way you measure the marker's position, you have a camera on the inside of the finger, and then you're okay. So
yeah. So we have, so the idea was to have as high of a density as possible. So we have a field where we measure that strain field as nicely as possible. The same way you will use a camera with a higher number of pixels, right? And initially we're going with piezoresistive solutions and things, and it gets really complicated really quick. And then you spend time working on the sensor rather than spending time working on the. And so now, you know, we piggyback on camera technology, which has been engineered to spend, you know, a huge amount of information from you know the natural world to the digital world. And yeah, so working on the idea is that the markers are doing the mechanical to optical conversion, and then the camera is doing the optical to digital. And yeah.
Just a take on what do you think, how fast do you think this can go, the whole thing? Like from, I want to grasp, like I go in contact, I initially really get in contact to, I know how much force I need to apply, and I can regulate that force.
Yeah, so right now the loop itself, so the P controller is only at 50 hertz, right? So it's really slow somehow. And it shows, because sometimes you get oscillation, probably because you're pressing too hard and it goes out. So how fast we go, we are mostly limited by, so one by the cameras, the camera 120, but the network also, because the camera has the high resolution, the network struggles to compute the safety margin. So it's mostly a compute problem. I think, yeah, with better camera, better network, more optimized, we might go faster. But yeah, it's going to be a lot of work to go like to 1,000 hertz, let's say, to much quicker.
That event cameras, do you think that those can be?
Yeah. So I think Nathan Nepora or someone from the gel site community also showed that, and yeah, we've been thinking about it.
Very relevant, because you only care about motion, right? You don't really any other information. So in that case,
no, it's true. No, it's definitely a good idea. Yeah, something we haven't explored yet.
Very much.
Maybe we will. Thanks.
A really nice talk. Just to reconnect like the human and the robot in the end, do you think that objects that are difficult for a human to grasp and that slips from a human are also similar in the robot?
Like the difficult thing, yeah, it might be. So the thing is, I don't quite know what I mean, nobody really knows what the network sees, right? So we might, you know, human might have different kind of perception. Maybe the logic of having just a P controller, proportional controller is the same, but maybe the perception or like this sensing, this unconscious perception might be different. I haven't tried it, so it's interesting, like maybe figure out. It would be nice to find like an object which is difficult to grasp for human, but the robots don't struggle, and then vice versa. Yeah, I don't quite know. It's a good question.
Any other question?
It's time for break then.
I just got one, so you won't get away that easily. So the compact base, it's quite simple in a way. They look like cable filters.
Yeah, yeah.
Only perhaps second to third order.
Yeah.
I was wondering how does it scale to the extremely high density of mechanoreceptors that we have, but how do you relate this to the density of matters you apply to these sensors?
Yeah. Yeah, so it's true. They look like a Gabor filter. So it's also the thing we put in the paper, which is kind of remarkable because it's a big thing in vision, right? So there's a bunch of Gabor filters for edges. And so the one thing is, I think the information, if you think about the information going in, I think it's going, so there's a lot of information coming in from the mechanoreceptors. But you need to take a decision really quickly. I mean, if something is slipping, you need to take a decision really quickly. So the idea would be with this filter is just to throw out most of the information and just look at most of the redundancy and just look at the main patterns. But I think for perception, you will get more of the perception, more of the initial bulk of information that goes up to the brain. So it might be a way to have, quick filtering, and then later on you can get a better image somehow. Yeah, that was one part of your question. And
about the density in your senses, the density of markers.
Yeah, so that's the thing. The same thing. Right now we're limited by what we know, by the fabrication processes. But if we could have way more, we will do it. Actually, we are doing a different way now, and which I didn't present, and which should be like a factor 10 on what we have now. Yeah, the higher the better, huh? Yeah.